our lecture series on real analysis. In this lecture, we are going to see one more result on compact sets. Let us get into the lecture. Here, you may notice that we are taking a subset in Rk, which means here this Rk is equipped with the metric that is standard Euclidean metric. Okay, whenever a metric is not spoken in the theorem, it must be understood that it is defined with the standard metrics on the particular sets. Okay, if it is given to be Rk, we have to assume that it is defined with the standard Euclidean metric, right? Under standard Euclidean metric, this Rk becomes a Euclidean space, and in that Euclidean space we are taking a set. Okay, if the set has one of the three properties, then that implies it has the other two. So in order to prove this theorem, what we are going to do is that first we will assume A and we will prove this A implies B. Okay, then assuming B, we will prove this implies C. Okay, then assuming C, we will prove this implies A. So from this, what you can get? You can go in either way, right? So by proving this, you can also say that A also implies C, C also implies B, right? And B implies A as well, right? All those implications are coming through this, right? So this is what we are going to prove in this theorem. Let us get into the proof of this theorem. Okay. Here, first thing, what are we assuming? We assume that a set E is closed and bounded. Okay, this is the assumption. With this, we need to prove what? We need to prove this set is compact. Okay, for this, E is taken to be some closed set, right? So this is closed as well as bounded. With this, can you identify some bounded closed set inside a Euclidean space? Yes, we can always identify a case which is bounded as well as closed, right? So since this is true, there is some case such that this E is contained in I. We are not saying only the K cells are of this sort, okay, but we can identify some K cell such that this set is contained in I. Okay, in this way we can identify some K cell, and we know that what? K cells are compact. Okay, so we know K cells are compact. If we know K cells are compact, now we are going to use the result that K cells are compact. Now you can see this is some closed set, closed subset of a K cell. Okay, we know K cells are compact, and also closed subsets of compact sets are compact, right? Of compact sets are compact, right? And this is why we can conclude that E is compact. Okay, here just because E is given to be bounded, we are able to identify K cell because K cells are bounded, right? Whatever may be your set E, you can identify some K cell which can be fit inside that K cell. Okay, you can choose the K cell large enough to fit the set inside, right? And E is given to be closed, and you may treat this E to be the closed subset of the K cell. Using the results that this K cell is compact and this is a closed subset of that K cell, we may prove E is compact, right? So let me erase it completely, and you can see the things on the screen as well. Okay, next what we are going to assume is that we are going to assume E is compact, right? E is a compact subset of what? E is compact in Rk. And in one of the previous lectures we have proved that if E is a compact subset, every infinite subset in E has a limit point in that theorem. Using that result we are going to prove. That is, we know that if K is a compact set and E is an infinite subset of K, then E has a limit point in K, right? So we have proved this result for any metric space. There we have not restricted our domain. We have not restricted our metric space. It was proved to be true in any metric space, and here in particular we are talking in Euclidean space. Okay, the same thing we have to prove, right? Any infinite subset of E has a limit point in E. That is what we need to prove. It is the same thing here. So there is nothing new to prove here, right? Next, what we are going to do is that we are going to assume this statement, that is what? Every infinite subset of E has a limit point in E. This is our assumption, and we need to prove the set E is closed and bounded. Okay, here we are going to prove this by contrapositive approach. First, let me assume E is not bounded. Okay, when E is not bounded, what is the case that we are going to have? We will have then there exist elements in E such that absolute of xn bigger than n for some n runs like this. Okay, and let me take S to be the collection of xn such that this is the case. Okay, and what kind of set it is going to be? This is then S is an infinite set, right? You have to note one thing very clearly here. Here we are talking about the points in Rk, not in any general metric space. We are particularly talking these things in Rk. So in Rk, some set is not bounded means that you may identify some points of this form. Okay, it is just the notation. Xn is just the notation, and based on this n, you may identify several points. You are collecting these points inside the set S, and you may always observe that this is turning to be an infinite set, right? Okay, now can you find the limit point for this set? Here just a minute. Okay, this set S does not have any limit point in Rk itself. The set is not going to have any limit point in the entire Rk. If it is not going to have any limit point in the entire Rk, then for sure it is going to have nothing in E. But what is our assumption? Every infinite subset of E has a limit point in E. Okay, here E is assumed to be not bounded, and there exist elements in E of this form. Okay, so from E only we are collecting these points and putting those points in S. So S is an infinite subset of E which does not have any limit point. It is a contradiction to our assumption. Therefore what? This implies E must be bounded. Right? So next it is left to prove only that E is closed. Let us do that now. Okay, even further, what we are going to assume that E is not closed. Okay, whenever we assume E is not closed, what do we actually have? We cannot come to the conclusion that E is open, because there are some sets which are neither open nor closed. So we have to think for the definition of an open set as of now. Every limit point of that set is a member of a set. That is the definition of a closed set, right? Here the set is assumed to be not closed, which means there exists some point, some limit point of the set, but that is not a member of the set, right? So that is those points we have to say. Then there exists a point, let me take that to be some x naught. Okay, there exists some point x naught which is a limit point of the set, but it is not a point of E. So this is what we have assumed, right? So with this assumption we will have to proceed further. Okay, next let me construct some set S to be the collection of points xn such that absolute of xn minus x naught is less than 1 upon n. Right? Here I am collecting these points from the set E, and n runs 1, 2, 3 and it goes this way. Right? Okay. Now what kind of set this S is? The set S is infinite, right? Because suppose if it is not infinite, then what is going to happen? After some stage here, we will have this value to be constant, which in turn will give you that this point becomes the member of E. But we have assumed that this is not a member of E, right? So clearly the set is infinite and x naught is a limit point of E. Okay, so this is not a limit, this is a limit point of S, because we have in the assumption itself we have taken that and that is the limit point of E. Okay, this x naught is also a limit point of this S, right? Now we are choosing one more point in Rk. We are choosing some point in Rk and it is not same as x naught. Okay, then we need to prove this y is not a limit point of S. We have to prove this, right? By proving this, we may come to the conclusion that, okay, we may come to the required conclusion. Okay, here in order to prove it is not a limit point, I have to say in the neighborhood of in some neighborhood of this point y, I don't have any point of this set, right? We have to make use of the definition of a limit point. What is the definition of a limit point? Every neighborhood of that point contains several points, right? That is the thing. Actually, in definition we have said it contains at least one point of the set, but immediately the next result tells you that it will contain infinite number of points, right? Okay, So what is going, let me consider absolute of xn minus y. Okay, sorry, wait, okay, I am considering right only. Let me introduce, add and subtract this thing with this. Okay, so I am writing in this form. It is just a matter of convenience, right? And we know, in general notation I am talking, absolute of a plus b is smaller than or equals absolute of a plus absolute of b. Similarly, absolute of a minus b is smaller than or equals absolute of a plus absolute of b. But what is absolute of? It may be either plus or minus, I don't, it doesn't matter. It is bigger than or equals absolute of a minus absolute of b. It is one of the results, right? So it is the basic results that we have for the that is in the properties of absolute function. So using that, we have something of this sort, right? Using this I have split these things. What is absolute of xn minus x naught? It is less than 1 by n. But what do we actually have here? This thing, right? So let us see what is the value of this thing. Okay, some of you might have got the idea now itself. So it is xn minus x naught is less than 1 upon n. So when you just negate the sign, you will have what? It is going to be bigger than minus 1 upon n. So this has to be replaced with minus n. So this is going to be absolute of x naught minus y minus 1 upon n. Right? I am telling this is bigger than half times of absolute of x naught minus y. When will it be true? Will it be true for all the values, or will it be true for only the selected values? Okay. Now you will have to think for a moment. Okay. Here actually what we are doing is that absolute of x naught minus y minus 1 upon n is bigger than half times of absolute of x naught minus y. Maybe bigger than or equals. That doesn't matter, right? Okay. When is it going to be true? And you have to remember one more thing, that we have chosen y as different from x naught. So these two values, as of now, if you forget about this quantity, what you will have, this quantity and this quantity may be equal. This will be equal only if these two are same, but that is not going to be the case. In general, what we will have, absolute of x naught minus y is always bigger than half times of absolute of x naught minus y, because these two are positive real quantities. So this is the general result we have. But what we are saying here is, even though I subtract some quantity, I am getting it to be true. When will it happen? It will happen only for certain values, not for all values, right? So this is okay. Your absolute of xn minus y is bigger than this thing for all, but infinitely many values of s. What do we mean by for all but infinitely many values of s? It is not true for all, but infinitely. That tells you what? For only for finite number of terms it is going to be true. Okay, for infinite number of terms it is not going to be true. Here what we have actually done, we are trying to find out the neighborhood. Okay, how many points are satisfying this condition? Okay, here it is becoming large, which means what? Only the finite values are going to present in the neighborhood of this y, which in turn gives you that this y is not a limit point of s. Okay, this concludes that y is not a limit point of s, which means S has only one limit point, and that limit point is x naught. So by this, what are we trying to say? We are trying to say that this S has only one limit point x naught, but that is not present in E, and S was supposed to be the subset of E, right? Okay. The things that I have told just now, let me put that in a wordings for which I need this page. Let me have those things as it is, and let me write that in different color so that you will not get confused with the flow. Okay. So by proving this, what we have proved? We have proved y is not a limit point of S. Okay. So here, what do we actually have? What we have is that we have an infinite. Okay, let me write that too. Okay, here we have an infinite subset S of E, okay, which has only one limit point x naught, but x naught is not a member of E. This is a contradiction to our assumption, right? What we have assumed is that every infinite subset of E will have a limit point in E, but here we have an infinite subset of E which the limit point of this infinite set exists, but that is not present in E, which is a contradiction. Okay, we get a contradiction. Therefore, what our assumption must be wrong, and this tells you that your E must be closed set, and this completes the proof of this theorem. Okay, you might have noticed that while we started compact sets, we have not discussed any examples of compact sets. We have seen around 9 results, I suppose. Okay, we are going to discuss one more result in compact set, and after that we will start working out problems on compact sets, because these results are going to play a very major role in identifying the compact sets on any metric space. Okay, and in this course we will deal mostly with the compact sets on Euclidean spaces, right? There are maybe few examples in other metric spaces too, but primarily and mostly we will focus the examples of compact sets in RK. Okay, and mainly this result, the result that we have seen in this lecture, is going to give you a very clear idea of what compact sets can be in a Euclidean space, because here this clearly tells you the idea that if a set is closed and bounded, that is going to be compact. Here we have proved these 3 equivalence statements, right? The equivalence of 1 and 2, that is, in Euclidean spaces a set is closed and bounded if and only if it is compact. If you put that in that way, it is known as Heine-Borel theorem. Okay, let me write the spelling. Heine-Borel theorem, right? So, and we have come to the end of this lecture. If you have any queries, you can post it in the comment section. That will be clarified within 24 hours of time. Thank you for watching.